one, the fact that the capacitance is equal to the charge divided by the voltage. So I need to figure out what is the voltage difference between these two charges, because obviously I know what the charge is there. I am going to use the relationship, another relationship we have done. The fact that the voltage difference is just the dot product between the electric field and my radial, my displacement. My electric field is not constant, so I can't just bring it out and just do E times the difference in the radii. That brings up the point of what are the radii. Let's make the inner one A and the outer one B.
Is B from the center?
Yes, B is from the center. Again, despite the way I drew it. So what is this doing today? Okay, all right. So the approach I'm going to take on this particular problem is to start with finding the electric field. If these charges are evenly distributed over the surfaces, then my electric field is based solely upon this one right here. That the outer one contributes absolutely nothing to the electric field inside of it because of spherical symmetry. I know that the electric field between A and B, so from A to B, therefore, well, we could use Gauss's law, or just exploit the symmetry and the stuff that we already know, that if I'm outside something with spherical symmetry, or spherically symmetric charge distribution, then I can treat it like a point charge at its center. So this is going to end up being 1 over 4 pi epsilon sub naught, or K if you prefer, times negative Q over R squared. In other words, the electric field is pointed inwards. That's my electric field. And so now, I'm going to be going from the inner surface to the outer surface. I'm going to be going from A to D. So the question is, let's start out with, will my answer be positive or negative when I find the voltage?
Should be positive,
Why?
because the equation has negative in it and our electric field is negative.
Yeah, but other minus signs can pop up as we do integration.
Voltage is the opposite direction of your electric field. Is that
Okay, so it increases as you go the opposite. Okay, I'll buy that. Or I was thinking more simply, you're going from the negative sphere to the positive sphere, so we should get a positive voltage.
Yeah.
It all fits together. All right. So this would be the negative, actually, that negative, now we'll stick it in there, from A to B. dr is in the direction of r hat. So let's go through the formality. 1 over 4 pi epsilon sub naught. Negative q over r squared r hat dot dr. Well, dr is the differential going in that direction, in the direction of r hat. So that would be r hat dr. So r hat dot r hat, those are my two vectors. So that should, they're unit vectors. And dot product with itself is just 1. So that negative and negative cancel out, and so I'm left with the integral from A to B, 1 over 4 pi epsilon sub naught, q over r squared dr. And pull the constants out, so Q over 4 pi epsilon sub naught. Integral from A to B of r to the negative 2 dr. Or 1 over r squared dr, depends upon how your mind works on that. Personally, I prefer the exponent, but that's just the way I do it. I'll be shocked if I don't screw up a minus sign somewhere in here. So that becomes r to the negative 1 over negative 1 from A to B. So I have negative q over 4 pi epsilon sub naught. That's the negative there, and then I'm left with 1 over b minus 1 over a. Did in fact we get a positive number?
Yes,
Why?
because b is greater than, well, b's in the denominator,
Yep.
so as b gets bigger, that value gets smaller. And since a is smaller than b, then that would be a negative number.
Yeah, so that difference is negative, cancels out with that negative sign, end up with positive. And at this point, it comes down to what form do you want it in. Typically, when I see this written out, it's written with just a single fraction bar, or at least not an addition, subtraction of fractions there. So that would be just this piece alone is a minus b over ba, or ab. And so with that minus sign, this ultimately becomes q over 4 pi epsilon sub naught times b minus a over ab. Now, we haven't answered the question. This is the hardest part of this type of problem, is trying to figure out that voltage. So if we now plug that into here for our capacitance, because that's the original question, it's Q divided by that. And so what you end up with is the Q's canceling out, and you're left with 4 pi epsilon sub naught AB over B minus A. And then I see if I get the same thing I'd written down here. Yes? Questions? All right. So that's it for the spherical capacitor. Let's tackle the cylindrical capacitor. Now, sorry, touching just slightly on realism here. I got the two conductors, one just magically suspended there in the middle. Potentially I would have some wires running through here in order to actually charge this, or somehow I got it magically charged and then build something around it. But you could also fill this up with some dielectric, which would boost the capacitance and allow for, then this becomes epsilon instead of epsilon sub naught. And then it actually could just be suspended within the dielectric. I'm still keeping that. All right, so now the cylindrical capacitor. That's spherical there. Again, we'll start with the radius A and B as before. And go with negative Q and positive Q. I'll make the middle one, the inner one negative. If we'd done the integration in the reverse order on the previous problem, we would have ended up with a negative voltage, but recognize capacitance ultimately is a positive number, so even if we had come out with a negative value there, we're just gonna do the absolute value in the end, or rearrange it so that we end up with a positive capacitance. So now I've got an electric field of this type situation. Let's actually use Gauss's law in order to solve it. So if I want to know the electric field in between here, and the electric field is heading towards the middle, I'm going to create a Gaussian surface that basically covers that inner charged cylinder. So I created a Gaussian cylinder more specifically of length L. Now we've gone through the derivation before of a single line of charge using Gauss's law, but we're just doing it again. So I know that my electric field at any point on that surface should be the same, especially if this is infinitely long. And the electric field will be pointing inwards because of where the negative charge is. And so I've got E dot A. Start out with the electric field inside. The electric field, the electric flux is equal to the charge inside divided by epsilon sub naught. Again, we're not sticking a dielectric in there. It's just magically suspended. Because my electric field is constant everywhere on this surface of radius r, then I can just factor that, let's put it in the intermediate step. So this is the integral of E dot dA. So I've got this can, the electric field is perpendicular to the sides of it. The end caps, the electric field is perpendicular to the area vector. On the end caps of my Gaussian cylinder, my area vector is pointing outwards, but my electric field is still perpendicular to that, so the dot product is 0. So this ultimately becomes the, well, E dot dA end caps plus integral E dot dA side. That's 0 for the same reasoning as we did last time we did this, but again, because the electric field and the area vector on the end caps are perpendicular and dot product is 0. My electric field is constant everywhere on the side at some radius r, and so I'm left with E times the area dot A is equal to my internal charge, which is, well, I have negative Q there, probably better since I've got this infinitely long cylinder, is instead of doing Q, do it in terms of charge density of lambda. So I've got negative lambda charge density here, and on the outside, lambda. Lambda is just Q over L. And so my enclosed charge in this particular Gaussian surface is going to be lambda times L. Yes, negative lambda times L over epsilon sub naught. My surface area of the side of this can, or of cylinder, is going to be just the circumference of the end cap times the length. So this becomes E times 2 pi r L is equal to negative lambda L over epsilon sub naught. L cancels out. And so I'm left with my electric field being negative lambda over 2 pi epsilon sub naught times R. Played a little fast and loose with the signs there. I know my electric field points inward, so however you want to deal with that. And so now we go back over there. Once we have our formula for the electric field, we can now find the voltage. Negative integral from A to B of, well, I know E is going inwards, dr is going outwards. So there's a negative introduced there. And so we end up with EdR, which is the integral from A to B of lambda over 2 pi epsilon sub naught R. And so pull out my constants, lambda over 2 pi epsilon sub naught, integral of 1 over R dr from A to B. And what is that integral?
Natural log of R.
A to B. So we get lambda over 2 pi epsilon sub naught, natural log of B minus natural log of A, which is lambda over 2 pi epsilon sub naught, natural log of B over A.
And that's just your delta V.
Yep.
Okay.
So the capacitance clearly has to depend upon length, because I've got Q up there and I've got lambda down here. I know lambda is Q over L, whatever the length happens to be. So I can change this into delta V is equal to Q over 2 pi epsilon sub naught L times the natural log of B over A. And I end up with 2 pi epsilon sub naught times L over natural log of B over A. Which would be negative 2 pi epsilon sub naught L over, I'm sorry, times, no.
I think
I was thinking that,
if you leave it that way, it kind of makes sense to me, because B over A, the closer that gets to 1, the bigger your capacitance is.
like shortening the distance between them.
Between
Okay.
the two radius, yeah.
Yeah,
Which is kind of the same rule for the parallel plates and the sphere.
yeah. And it does depend upon the length, because obviously if I have a really long one, I'm gonna have greater capacitance than if I have a short one. And then I check to see if I screwed up the negative sign somewhere. So it's C over L, 2 pi epsilon naught over the, yep, that's what I had. The only difference is I guess I officially, in my notes, I found the capacitance per unit length, so divide by L. All right, questions? Now I assume the chapter 27 master set is gonna be a lot easier now.
Had to read ahead, I was reading, and I was like, this is nothing like this. I don't know why I didn't get it in, but I figured it was one of those, well, it wasn't on a study guide, it wasn't on, and it wasn't on the test kind of deal. They're two separate things.
I'm glad we resolved that mystery. All right, I think I'm done with 27. Obviously, we have not had the test on through 26. But that'll get changed soon. See, 27, yeah, so they got this formula, they got the parallel plate capacitor stuff, which we've done. They didn't throw a dielectric in at that point. But they did there.
So what chapters is the test covering, just to make sure?
23 through 26.
Okay.
But some of the older tests will also have some of the parallel capacitor stuff in it, just because the previous textbook threw that into a slightly earlier chapter. How many of you had E&M, whether part of high school physics or up through now, have had E&M before? Electricity and magnetism? The parallel and series capacitors. Anybody, have you dealt with that in a previous class?
Yeah, I had an engineering course at Clemson that was
Okay.
kind of tailored to that.
Sorry, just wanted to see where people are. All right, so the next bit is, I mentioned earlier that it's all about trying to control current flow, so let's actually talk about current flow. And we will derive a formula known as Ohm's law. And even after we have this new formula, recognize we still have only one physics formula that we've dealt with in this course. Coulomb's law. That is the only physics formula. The rest of it is definitions and math. So it gets more and more disguised as we go, but it's still at the core of it, Coulomb's law. So if I have a wire here, and I've got some sort of monitor